Thanks, everyone. So I'm Matt, and I'm going to be talking about, well, this was the title that we made for the tutorial, at least, composing graphical models and neural networks like chocolate and peanut butter, which is a phrase that reminds me of my friend and collaborator, Matt Hoffman. So this YouTube link goes to a commercial for Reese's Peanut Butter Cups from 1981, and I wish I could show you that video, but I think Google doesn't let me show like potentially copyrighted things when I give presentations. But watch this. It's an ad where like two people are walking along. One person's eating chocolate, the other person's eating peanut butter, and they like bump into each other, like get their chocolate and peanut butter all mixed up, and then they taste it, and it's like amazing. That's what deep neural networks and graphical models are. You got chocolate in my peanut butter. So as I prepared for this tutorial, I realized maybe a slightly more accurate title would be something like this. Graphical models and exponential families in the age of differentiable programming. So, you know, deep neural networks, people like to say, well, really, it's all about differentiable programming. And I realized that I don't have that much to say about deep neural network details. But I do have some things to say about automatic differentiation, which is sort of like the workhorse that powers deep neural networks, and how graphical models and exponential family ideas might be able to leverage autodiff and work with it. So that's what you're going to see in this tutorial. So let's start by just outlining some goals and sort of what's in it for you by attending this tutorial. So my first goal is to motivate all of you, to sort of inspire all of you to say why PGMs and deep neural networks, putting them together, is a revolution waiting to happen. After I wrote that, I realized this is a bit strong, the phrasing, but I do think that there's a lot of really interesting, compelling potential here, like a lot of big things waiting to happen in science, in like robotics and control, in putting these things together. So I hope to convince you of that, if not a revolution, at least some things worth thinking about. The second goal of what you should get out of this talk is I'm going to give a survey of the fundamentals of graphical models and exponential families to really give you a broad view of the territory. So there's a lot here. I made too many slides. And so as you watch the math fly by increasingly quickly as I go through the presentation, the point is not to be able to dig into all the details, but hopefully you might see some things that spark your interest. If you're new to the field, maybe you'll say, hey, that seemed really interesting, I want to follow up on that. Or if you're sort of old hand, you've been doing these things for a long time, hopefully there's something new in there for you as well. In particular, I want to show you a sort of unified view of how to think about these things in the context of automatic differentiation and like how we can write software effectively. I think that the sort of graphical models and exponential family ideas that you're going to see here have not had their sort of automatic differentiation moment. So deep learning was, it was sort of hard to do deep learning research before we had automatic differentiation and like GPU accelerated tools. And then when we got those available, it was like a garden of delights. It exploded in power and in terms of the research people were able to do and the ideas they were able to have. And I think that moment is yet to happen for graphical models in the sense that when we get the right tools that can leverage autodiff and accelerators, I think there's a lot of potential to be unlocked there. I don't think we're quite there yet, but you'll see some ideas in this tutorial. So the last goal, my real goal, the fourth goal, should I tell you, now that I have you all trapped here and listening to me, should I like reveal my secret evil plan, why we're all really here? So I did some work on graphical models plus neural networks that we called structured variational autoencoders. And there's really a lot of work in this space. And the most common feedback that I get from that work is, seems cool, but it's a lot of math. Like your appendices are like 20 pages longer than the paper. So, did it have to be that complicated? And, maybe not. But hopefully by the end of this tutorial, you'll see that I want to make these things super obvious to everyone, so it's like, oh man, that was an obvious idea, nothing really super hard there. And in fact, hopefully you can come up with better ideas to move things forward. So that's my secret real goal, is so that you can improve on all this stuff and fix it up and unlock our new PGM plus deep neural network feature. I just remembered I was supposed to mention the slides are now online as of like an hour ago. So if you want to look at these, you can go to the UAI website and you'll find a link to these slides, except for the bonus slides at the end, which I added just before coming here. So those are goals. Here are some non-goals. I'm not going to do a good job at all of surveying the recent literature, in part because I don't know it super well. I've been sort of like sidetracked to working on systems and tools. I'll mention a bit about that at the end. This is not going to be like a survey of recent works. I'm really going to focus on the fundamentals. And the other non-goal is you're not going to step away from this and understand all the technical details, because back in my day, I took a course on probabilistic graphical models for a semester. Has anyone here taken a course on graphical models? That's perfect. Great. So hopefully you'll see something new, but hopefully for everyone else, you'll just get a flavor for sort of what it's about. So let's start with motivation. And to motivate you about why these kinds of models and techniques might be interesting, I want to tell you how I got motivated to combine deep neural networks and probabilistic graphical models. And it starts with this guy. This is a mouse. This is a mouse on a lab bench in a neurobiology lab at the Harvard Medical School. And the neuroscientists there study mice. They study the mouse brain. This isn't just that they have like a bad mouse infection. They have hundreds of mice they use to study the mouse brain by understanding its behavior. Right? So they want to sort of study this mouse and do experiments on it and see how that changes its behavior. But how do you quantify behavior of a mouse, right? Like, what does that mean? You might imagine that you can come up with some heuristics, like count how often the mouse is in different quadrants of its enclosure, this sort of thing. And those are sort of the cutting edge techniques. But if you as a human are told to watch this video of a mouse, as I'm forcing you to do right now, I think you'll naturally come to a sort of description in your head of what the mouse is doing in terms of little brief stereotyped units of action that we call behavioral syllables. This is how ethologists think about mouse behavior. So they think about it as decomposed into little pieces that we might imagine attaching even English words to. So the mouse might sort of dart forward, or it might pause, or sort of curl up into a ball and groom itself, or it might rear up into the air and explore. And these little units of action, discovering these automatically from video would be analogous to saying, given an audio waveform, maybe in a language that you don't speak, try to discover the syllables, right? So if I said, try to discover, maybe from some kind of video recording of a mouse, what its behavioral repertoire is, what its sort of behavioral syllables are, that's very much analogous to saying, discover syllables, the syllables present in this speech. And the reason why you'd want to discover syllables is that then that's a representation that maybe you can, as a scientist, or you give to your friend who's a scientist, to study, right? So at Harvard, they wanted to do things like zap the mice in the brain with lasers, or control its genetics, or sort of expose it to natural or synthetic compounds like drugs, and study how that changed its behavior, right? And we can sort of instantiate that concretely as saying, if I can learn from a lot of data what the sort of behavioral units are for this mouse, then I can study when I make these sorts of changes, these interventions, how the mouse's behavior changes concretely in terms of, say, how the unigram statistics are up and down regulated, or the bigram statistics, like the transitions between these syllables. Just like how in speech, a lot, not all of the content, but you can start to get a sense for the content and the patterns by looking at the syllables and the sort of transition structure between them, and then see how those things change in different conditions. That's what we'd like to do to mice. So that was the challenge. How did we approach it? The first step was to get the mouse into a computer. And the way we did that was we used a Kinect depth video camera from above. This is a video from above of the mouse wandering around in sort of a bigger yet empty container. And so the color mapping here is height of the mouse. You can see him sort of rear up and this sort of thing. Don't worry about the speckle. We can get rid of the speckle stuff on the sides. So we would sort of track the mouse using a simple algorithm and then produce this video that you see inlaid in the top left, which was, that is sort of a egocentric version of a mouse's behavior, right? It doesn't matter which way he's oriented. We're just like, the head's always on the right, and we're recording this mouse in 3D. So when I say we wanted to learn a model for mouse behavior, Concretely, we wanted to learn a model for this kind of video, the video you see in the top left. So one way to sort of think about this video maybe is that there's some kind of an image manifold, right? We don't see all possible, even though the images are maybe 60 by 60, so they're very high dimensional image observations, we don't see every possible combinations of pixels, right? Maybe we only see a small subset and indeed like a manifold of images, so that every video frame lies on or near this sort of low dimensional manifold in image space. So then a video is a trajectory that lies on or near this sort of image manifold. So when we want to learn a description of these data, this is the sort of thing that we might want to come across, is somehow fit some kind of a model for this manifold. But we don't just want to learn the manifold as a set. We actually want to learn it in a coordinate system in which we can describe the animal's behavior in terms of these simple decomposed units of action. So imagine that we have some coordinate space in which the dynamics are actually fairly simple for each movement. And then that can give rise to extremely complicated nonlinear high dimensional data by sort of being dynamics, even though they started simple, being dynamics on an image manifold, and we get to see noisy images. That's just to give you a taste of like how to think, or at least how we started thinking about these data. So this is really a joint learning problem, because we can't just like learn the image manifold as a pre-processing step and then fit some kind of dynamical system. We actually want to learn it in a way so that our model for the dynamics in the low dimensional coordinates works well. So what kind of tools can we use to model this video and extract out this kind of structure that we need? One set of tools, an obvious one to reach for, is recurrent neural networks. I made this slide a while ago, so these references are super old. But there's a lot of work on modeling video. So maybe we can use neural networks to model video. The problem with using neural networks on a problem like on a challenge like this one is what we get out at the end is a whole bunch of weights and biases, and who knows what's in there. It's just like these big matrices. But we do know it can generate video really well, right? So we could generate more mouse videos from this sort of thing. That would be great. The problem is we already had a way to generate videos called undergrads. Undergrads will record as much mouse video as you tell them to. So we had millions of frames of mouse video. We did not want more synthetic mouse video. We wanted to sort of like parse that information that we had into some kind of organized representation. So these weren't quite the right tool. Then you might think reaching for probabilistic graphical models, which we're going to learn a lot more about. But the basic idea is that these things are useful for constraining and organizing information in a sort of prescribed way. But they can fall down when trying to model things like images. To sort of explain the way, one way to think about these two alternatives a bit more, I want to abstract things, simplify them, get rid of the complexity of modeling a mouse video and even time, and just think about a stylized representation learning problem. So here's a bunch of points in 2D. Maybe I tell you that they're conditionally IID sampled, and I say like, learn a representation for these data. You'd be like, well, it sure looks like there are clusters, and so maybe you'd fit a Gaussian mixture model. And indeed, those were just synthetic data that I generated from a Gaussian mixture model. So if you have data that come from a GMM and you fit a GMM, works great. Good. The problem comes when your model design is false, like it doesn't fit the data well, it's misspecified. So here's still a toy example, but just imagine here are data that still have this sort of clustering structure, but don't look like they came from a GMM. They came from a sort of warped GMM. Depending on how you set the hyperparameters, if you fit a Gaussian mixture model to this, especially if you let it learn the number of components using a Dirichlet process business, maybe it'll end up instantiating a lot of Gaussian mixture components to model the data density well. And maybe that's an okay model of the data density. Put down enough Gaussian mixture components and you'll be able to model anything. But we've lost what we wanted, right? We lost this sort of interpretable representation of states, right? These are kind of like analogous, these clusters are analogous to the mouse syllables. And this is a real problem that we had when we tried to fit more stylized models, sort of graphical model techniques. They would just use up all their capacity by sort of tiling the space because of model misspecification. So PGMs on their own don't work for even just like slightly misspecified data. how can we hope for it to work with things like image manifolds and all that? So another technique you could use is a variational autoencoder, or some kind of density network based on deep neural networks. And indeed, you could fit one to data like these, and it will do a great job learning the density. Maybe I should have run this for a bit longer. So this exemplifies, it's analogous to how we might expect fitting an RNN to a video of mouse behavior to work. It'll learn complex things like multimodal data and learn all the details here, but you don't know sort of what it's learned. Maybe you can sample from it. Maybe you can evaluate the density at points, but you don't actually have sort of surfaced to you the idea that there are actually multiple modes that have been learned, right? You're just looking at a bunch of weights and biases and stuff. And the fact that it's learned some complex data distribution is just a black box to you. So in this case, the fact that we don't get to see the clusters explicitly represented, that's sort of problematic. It's just a density model, but that's not what we want. So what we really want is some picture like this, right? That sort of combines the two, where we can have a flexible density representation, yet at the same time, maybe learn these mixture components. So this is a stylized picture to keep in your head of one version of PGMs plus deep neural networks. Actually, there's I think a very good analogy to what we do in supervised learning, which is to say, in supervised learning, what we do, even with kernels, but with deep neural networks, we have data that aren't linearly separable, right? They don't play by the rules of our simplified models, but that's okay. What we'll do is we'll stack up a whole bunch of feature transformations, and then at the end of all of our features, if you look at the last layer of any neural network, well, not any, simple neural networks, it'll just be a sort of linear classifier, right? So the whole purpose of a neural network is to sort of move our data around, do nonlinear transformations, so that a simple model like a linear classifier will work. We sort of want to do something analogous in this unsupervised learning domain, where we want to say learn a transformation of our data space, produce features in which a model, maybe like a Gaussian mixture model, will fit well. So to summarize, I think graphical models have a lot of good things going for them. They have these sort of, they give us ways to organize and constrain probability distributions, which means organizing information in a useful way. They're also really great at us, helping us write down priors and uncertainty, because maybe we understand how to encode information a priori. But the problem is that the rigid assumptions don't fit, and so oftentimes we end up in this, or we used to end up in this terrible area of trying to do feature engineering, which was problematic. On the inference side, that's sort of like the modeling side, but on the inference algorithm side, they also have some interesting things going for them. Especially, they're sort of like computationally, they can be quite efficient. So you can do graphical model inference sort of at test time, if you like, and support many different inference queries, not just one. We'll unpack that a bit more later. But these things only work in these very rigid model classes that are too constrained. Alternatively, sort of deep learning kind of techniques, when you fit a deep learning model, what you get out might be sort of this neural net goo, to use Kevin Murphy's phrase, just like a bunch of stuff that models your data, but you don't know what's going on inside of it. That similarly means that we don't know good ways to put priors on these. But we love deep neural networks because they are so flexible and they let us model complicated data like images. I think there are interesting things to compare on the inference side, but maybe the most exciting development, 5 years ago now, is that sort of recognition networks can learn how to do inference for us, as opposed to how we used to do inference. So as you can see, by comparing these two columns, I think there's a good case to be made that these sort of strengths and weaknesses are complementary. And so, broadly speaking, I think we should, work on how to combine these strengths and weaknesses. Very similar to how the last tutorial sort of, a theme of the last tutorial. How can we use, simpler structures embedded in more complex ones to maybe push the boundaries of what we can do? So that was it for motivation. Let me make sure I'm looking at the time. Okay. That was it for motivation. Let's move on to survey the fundamentals. So again, I'm going to go through some of these things kind of quickly, but take this as a way to sense what might be interesting to you. Let's talk about graphical models from scratch. So what graphical models are about, sort sort of the axiomatic theory of graphical models, is ways of taking graphs, which are these combinatorial objects, and relating them to probability structures in two ways. The first way is by giving them a sort of semantics in terms of conditional independence among random variables. And the second way is to say, actually, this graph is going to describe some kind of algebraic structure in my probability density. So assuming that we have a probability density for these things relative to some measure, I'm not going to say the word measure again, you should call me out if I do. Assuming you have some probability density, one way of giving graphical models semantics is to say that they describe some algebraic structure in that density. And these two things are almost the same, but not quite. So let's unpack that. What is a graph? So here's an undirected graph. We're going to start with undirected graphs. A graph is just a pair of a vertex set and an edge set. The vertex set is going to be boring, just like a sequence of integer IDs. And then the edge set, I like to write it like this for undirected models, where it's a set of sets, just to clarify that the order doesn't matter. So there are these edges from node U to node V in the edge set. So here's an example. Here's that one simple example. Our vertex set being 1, 2, 3, and our edge set being 1, 2, and 2, 3. So how do we take undirected graphs and give them, and use them to ascribe structure to probability distributions, to collections of random variables? So here's a definition. We will say that a collection of random variables is Markov on a graph if you look at any triple of disjoint sets of nodes. You say, if I can delete the set C, and that means that there's no longer any path from set A to set B, then I'm going to say that A and B, those subcollections of random variables, are independent given C, the one that I removed. So disconnects means there's no more path. Let's just look at some simple examples. I think you'll know how to generalize it. Here's again our simple graph. This thing is implying the conditional dependence assumption, the statement that given x2, x1 and x3 are independent. So in general, graphs imply sets of conditional independence assertions. This one is saying that x1 and x3 are independent given x2 and x4. But not if I just condition on x2, right? Because if I just delete the node indexed 2 in this graph, then 1 and 3 are still connected. So connectivity in graphs and independence. So here is that was the random variable view of graphical models. Here's the density view of graphical models. We say that a collection of random variables factorizes, or its density factorizes, on an undirected graph G if its probability density can be written as a product of factors that only depend on variables corresponding to cliques in the graph. So clique is a subgraph that's fully connected. It's a complete graph within the graph. So it's like, I think it's called a clique because when you have a set of friends and they all know each other, but maybe they don't know you, that's like a clique of people. So the idea is that the algebraic structure and the density is that we can write it as a product of cliques on the graph. So here's again our super simple Markov chain example where we say when we say that a density factorizes according to this undirected graph, what we mean is we can write its probability density in this way as a product of just terms that one term that depends on x1 and x2 and another that depends on just x2 and x3. And by limiting that dependent structure, that's saying a statement about something. So here's another graph. What are the factors that I can write this density in terms of? Perfect. I heard the answer twice, or there's an echo in here. Yeah, indeed. So the 1, 2, 3 and the 1, 3, 4. Either you guys have taken a graphical models course, or you're very quick on the uptake. So that's the two definitions of how to relate a graph to structure in a probability distribution or a collection of random variables. Are these the same? I already told you the answer. They are not quite the same, but there's a theorem called the Hamersleycliff theorem that says if the density is positive everywhere, maybe there's other technical conditions, like it has to be finite, I'm not sure. But basically, if the density is positive everywhere, then these two are the same thing. Then saying the conditional dependence assertions and the density factorization statements, those all hold true no matter what. The trick here is to like have some density with zeros in it, right? Or like log density with negative infinities. You can see how to break this thing. So that's undirected graphical models. I'm going to talk a bit about directed graphical models, but before we do, actually you can already see the emergence of these exponential family things, little hints of exponential families here already. And here's how to do it, how to sort of see these hints. So if you want to make your density positive everywhere because you don't want to worry about these sort of pathologies that happen, one way to do that is to say, I'm going to make my density be exp of something, like exp of a negative energy function. That's great. And so then, if we think of the energy as the sort of log of the density, then we see, I don't have a mouse cursor, but like on the second line here, we can think of this product structure as turning into a sort of sum structure. Now that we have this energy written as like a sum of all these local potentials, or log potentials, now you might wonder like, hey, without changing the graphical model structure, I could generalize this to consider all linear combinations of those instead of just one combination, and then I'd have a family of distributions parameterized by these coefficients that I put on them for the linear combinations. A whole family of them, and there's an exponential in there. So this is a hint that graphical models and exponential families are intimately related. So that was undirected graphs flying by quickly. Let me tell you a bit about directed graphs and how we ascribe semantics of collections of random variables to those. Similarly, there's a way to talk about independence. There's also a way to talk about algebraic structure. So to start with, a directed graph is also just a pair of a set of vertices and a set of edges. And the edge set here is a set of pairs, right? In the other case, they were just a set of binary sets. So here's a simple example, as before, where now the edge set is the ordered pair 2, 1, and the ordered pair 2, 3. So here's the first way to talk about random variables being Markov on a graph G. It's similar to the other one where there's a kind of separation where you say, okay, look at 3 disjoint subsets of random of nodes in my graph, and we're going to say that the set C d-separates, that stands for directed separation, I think, d-separates A from B. If that's the case, then we'll have this conditional independence assertion that the random variables in A are independent of those in B given values for the ones in C. So d-separates is very much like, it's analogous to undirected separation, but with a twist where we add just to make things work out correctly. So separation is all about paths. So when you're looking at all the paths that you might be able to follow from the set A, from some node in the set A to some node in the set B, we want to decide if that path is sort of blocked or not. And if all the paths are blocked, that'll mean that this independence assertion holds. So here are all the cases when you're walking along a path, you'll run into little triples of consecutive nodes. And these are all the possible cases that you can run into. Which ones are blocked? You might think that all the ones in the bottom row are blocked because that's where it looks like there's sort of a filled in node in the middle. The filling in means we're conditioning on that value. Indeed, these are the ones that are blocked. There's a twist. The only thing you have to remember is that this special structure in the right-hand column, it has a special name. It's called a collider. And we give it the special rule that actually it's blocked if the middle node is not conditioned on, if it's not shaded, if it's not in the set C. And it's actually unblocked. It's opened up if you condition on it. So this is used to trip people up on tests. That's what we use this for. Just kidding. It's used to model some useful property about how conditional probabilities work. So here's an example, quite similar to what we had before, where we condition on 2. 1 and 3 are independent. Here is the opposite structure. So the graph, even though I drew the middle node down, that doesn't matter. The point is that the arrows are going into 2 now instead of away from it. And so this is that special collider structure. And that means that if we say that our distribution is Markov on this graph, x1 and x3 are actually independent when you condition on nothing, sort of marginally independent. And it's not the case that they are necessarily independent when you condition on 2. They might still be independent condition on 2, but that's just because graphs imply sets of conditional independence assertions, that doesn't mean that they imply all of them for the collection of random variables. So that was random variables, conditioning, and relating those to directed graphs. There's this other way of relating directed graphs to probability structure. That has to do with the density factorization. This one's really quite natural, even though the notation's a little bit weird. We say that a collection of random variables has a density that factorizes on a directed graph if we can write the density as a product over all the vertices of terms where we think of the conditional probability of, or the probability density of that node associated with that, that variable associated with that node, conditioned on all of its parent nodes. So PA here means parents of V in the directed graph G. So here's a factorization corresponding to these two different graphs. As you can see, they are quite different, and this is why we have a special rule. But you can see in this collider structure maybe already why, if I tell you a value for x2, in the former one, we get sort of a nice factorization in the top line of independence between x1 and x3. In the second line, condition on x2, somehow now we get this joint entanglement of x1 and x3. So, directed models. These directed models, you might have noticed, it's sort of everything is just parameterized based on its parent. It looks a lot like a sort of computation graph or something, right? It's sort of like a specification for how to maybe generate a sample. And indeed, you can actually say, if I have a directed graph and I'm not conditioning on anything, that sort of tells you a way to draw a sample. Just start at all the nodes that have no parents, and then sample values for those, and then sort of march down. For each node, when all of its parents are sampled, you can sample that value. It's called ancestral sampling, and that's sort of why directed models appear often with generative modeling, because they're just a very natural way to parameterize things in terms of sequence of steps. I won't go into the details, but there are beautiful connections between Gaussian graphical models and linear algebra and numerical linear algebra. And so this might be a little intriguing. Directed parameterization is like, or in fact exactly the same as having a Cholesky factorization, or a lower triangular square root. The Cholesky is the unique such one. So there are nice connections to linear algebra if you're into that kind of thing. Undirected models, on the other hand, I think of them as coming up much more often in inference, when you have an inference problem, because it's actually quite simple. When you have a directed model, everything's hunky-dory when you're just sampling from the roots, the ones with no parents, down to the leaves. But what if I condition on the leaves and ask you, what then? What kind of distribution do you have? And that kind of ruins all the directed structure by conditioning on things at the bottom. We can no longer, you can no longer draw a sample from that conditional distribution by starting at those nodes with no parents. So when we do inference, like when we ask, hey, you have that nice probability distribution, how about this conditional distribution? When we try to do inference in conditional distributions, oftentimes we end up working with undirected models. And you're going to see a whole lot of that later on. For Gaussians, these things sort of relate to linear system solving, if you like that. There's one more variant, which I don't think of as distinct from those two, but it's sort of like quite useful to know about. These are conditional random fields. And these are graphical models where the potentials depend on exogenous data. It just means that you don't have a graphical model until someone gives you data. Someone gives you data, and then you have a way of producing potentials in your graphical model. I should say these little factors, like these psi factors in the density, those are called potentials. So, for example, one way they're traditionally drawn is in the top left here, where we're sort of always conditioning on those nodes on the bottom. And the idea here is that it's saying, given values for these nodes on the bottom, then I have this chain structured graphical model. I don't like that way of drawing it quite so much, because you might think, do I ever have these nodes at the bottom unshaded? Am I ever asked to do inference over them? The idea is no, you're not. You only learn distribution parameterized by some other values. So here's another way to draw them, slipping into this kind of factor graph convention where we sort of just draw little squares, and we remember that those can depend on external data. In fact, this is already a way to combine neural networks and graphical models, these conditional random fields. This work sort of goes back decades at least, where you can say, hey, what if I came up with a graphical model by having a neural network or some parametric function approximator, and that's going to take in data and spit out graphical model potentials. So for example, if you wanted to optical character recognition, so you had a sequence of images, like the MNIST problem. You had a sequence of images that correspond to handwriting, and you wanted to estimate what the written characters were. Maybe your neural network can take in an image and generate a potential on it's sort of a guess for what character that is. And then you can have a hidden Markov model that's like a language model. The graphical model potential says, it says how compatible are these pairs of adjacent symbols that we estimate. That's a nice way of putting things together. I just want to be sure to mention that because that's a great way to combine graphical models and neural networks. When I talk more later, I tend to think more in the unsupervised generative modeling kind of situation, not this kind of conditional generative, conditional random field setting. These are great to know about. Here's another cool CRF, like a grid structure. Great, I'll skip over that. So that is, I'm trying to do math in my head from how much longer we have. Okay, so that was a sort of survey of the fundamentals of graphical models, and some people kind of stop there. Actually, oftentimes when you see the word graphical models in the literature, some people just use these things, using the semantics that we just talked about, as ways to organize information. And they're already quite useful because you can say, maybe I want to create a generative model where the pose of my mouse is decoupled from the instantaneous pose of my mouse is decoupled from some description of its body shape, right? And already you can imagine encoding that using sort of graphical model semantics by saying, well, the body shape will be sort of part of the latent code that doesn't depend on time, and the pose does depend on time. So I'll just have one random variable for each mouse for its body shape, and then for each mouse and each point in the video, I'll have the pose, and I'll sort of put those together. But I'll learn them as independent. That's, you don't need any more than just graphical models and some like variational autoencoder type neural nets to do that. However, I have a lot more to say about graphical models, especially exponential families. So there's much more in the toolbox from graphical models and exponential families to do with, especially to do with algorithms for inference. And when I work on these things, I'm like, how can we use as much graphical model technology as possible, especially technology around exponential families for inference algorithms? That's what excites me. So we're going to talk next about exponential family stuff. We're also going to start seeing a bit more about how to leverage automatic differentiation. There's been no autodiff so far. So let's start with defining an exponential family of densities. I don't want to say if you take one thing away from the talk, but I believe it is not the exponential family. It is an exponential family of densities, as I think will become clear when we look at this definition. But just use the indefinite article. It's like, I have an exponential family here. Okay, so n exponential family of densities. Let's build it up piece by piece. You can see this is blank right now. It's not because I didn't finish my slides. We're going to build it in one at a time. So think of an exponential family as really defined by a statistic function. And the statistic function goes from it's a function that takes in sort of the range or the outcome space of your random variable and maps to a finite dimensional real vector space. It's very important that it's finite dimensional. Otherwise, everything is an exponential family. So that's really going to be the sort of power. So we have the statistic function. And that, once you set up a statistic function, more or less the exponential family is defined and constrained. Everything else is just going to be a procedure from here. So then we're going to think of all energy functions that have this form. You take a vector of real parameters, and you say, think of all linear functionals, if you like, on that statistic and exponentiating them. This gives us an energy function. Right? So this will be a non-negative, real-valued, actually positive real-valued function, and we're going to use that to define our probability density. This also sets up a Lognormalizer, and so now this sort of completes the view where we're going to think of our density function on x parameterized by a natural parameter eta, which is just a vector of real numbers, as having this form where the sort of calligraphic A is the Lognormalizer or log partition function. And this is a function that takes in the natural parameters and it spits out a real number. And it's basically how to keep this energy function normalized. Here it is. The definition is just like a log sum exp, log integral exp. I haven't defined what theta is, but I will, I think, next. Yeah, that's good. Okay. So theta is just the set of all eta parameters for which this integral is finite. Right, so you might have values in your whole vector space where this value is finite. It turns out that actually this is a convex set, and A is a convex function. It's actually sort of, if you know that log sum x is convex, that's the same reason log integral x is convex. So maybe, you know, pathologies aside, this A is actually always a convex function of the natural parameter, and theta is always a convex set. So let's just move up our definitions there and say a bit of some interesting properties. I already spoiled this one. So A is convex. And here's something interesting. If you think about its gradient mapping, so A is a function that takes a natural parameter eta and spits out a real number. So the gradient takes in an eta and spits out something that's the same shape as eta. So the gradient of this Lognormalizer function actually gives you expected sufficient statistics where the expectation is over that probability distribution you've defined with this density. And actually, it's not hard to show. You can just differentiate it. And if you think about differentiating a log, right, log x, you get a 1 over x term, so we get 1 over the integral. That's great. And then we differentiate under the integral sign, which we, you know, it's very, we do very loosely, even though there's some kind of condition we have to satisfy to do that. And then, you know, we differentiate x, we just get, you know, with respect to eta, we just get a copy of t of x and then another copy of the exponential. So that's actually just, you know, the definition of the expectation of t of x. In fact, doing the algebra slightly differently, you can show that A, the log partition function, is directly related, almost the same as the cumulant generating function. And so higher order derivatives give you cumulants. And the second cumulant is just the second moment. So it looks like it gives you moments, but it's actually cumulants. So those are just sort of nice properties. I didn't define what the set M is, the sort of range of this gradient mapping. And M is actually, this is sort of an interesting line. M is the set of all expected sufficient statistics you can get, so expectations of t of x that you can form for any probability distribution. Not just these exponential family ones, but for any probability distribution. This is sort of a nice property because it tells you why these exponential family things are sort of canonical, because if I can always write some exponential family distribution, some member of my family, if I can always find a member of my family that can recover any expected sufficient statistic that any distribution can come up with, then I sort of feel like I'm not losing out on much. And it's almost true that this map is surjective. It's only, it can only possibly fail at the boundary, in which case you can take like a sequence of points. Those are interesting asides that I mention only in case you're into convex analysis. If you like convex analysis or you want to learn about it, thinking about exponential families is a great way to do it. To give you some taste of like other things we can write in terms of this Lognormalizer function, one other thing is the KL divergence between two members of the family. This is just, you can substitute in the definition. And in fact, a lot of different things, you know, a lot of different quantities really just come down to having this Lognormalizer function. I should mention that in the world of autodiff, these are not just symbols that we write down on slides anymore, right? You will see that you can actually just write this in your code. You can actually just implement this, you know, if you have an efficient way to compute the Lognormalizer for an exponential family, you don't need to implement a routine that computes the KL divergence between two things or computes the expected sufficient statistics. You just use grad, and that's all. You just use your autodiff. That's going to be a sort of theme you'll see more of in a moment. So I'm going to use this term loosely. This is one that I made up. I don't think it's super common. I'm just going to say family is tractable if the Lognormalizer is easy to evaluate. What does easy mean? I don't know, polynomial time or something. And like, you know, maybe there are other ways of being tractable, but this is the one we'll focus on. So here's an example of an exponential family, and you will see the intimate relationship with graphical models. Consider a binary hidden Markov model. Binary makes the notation simpler, but the whole picture generalizes. So consider a binary hidden Markov model, by which I mean we have a density that looks like this. So the etas are just scalars in this case. And so our density looks like x of a bunch of node potentials, if you like, eta sub 1, x1, eta sub 2, x2, and a bunch of pairwise potentials. So if our density looks like that, we know we can factor it in terms of these potentials. We have psi, is that psi? I think that's psi, right? These psi potentials. We can also write it, this is, I think, a tradition that you write psi for the exponentiated one and phi for the non-exponentiated version. But this is sort of talking about the same thing. So our statistic in our exponential family in this binary hidden Markov model, just you can write it as it's the sequence of all these phi values, right? And so the idea is that we can write down essentially any binary hidden Markov model by just saying, well, this is my statistic function. Consider all linear functionals of it. Exp of those linear functionals, that'll give me my density, right? So that's the statistic. I actually want to write the same, a related statistic. I want to write it in another way. So you can see that this is sort of all, ultimately this is based on all sort of like, this is like a big polynomial where we have the monomials x1, x2, x3, and we have the monomials x1, x2, and x2, x3. So here's another way we could think about writing it. Think about writing the statistic as this matrix, this outer product matrix. So this is going to form all the monomials, and along the diagonal we'll have xi squared, but because it's binary, that's just like xi. So this statistic is like all the different monomials of, up to sort of max degree 1, I guess, I don't know. So I'm just going to summarize that statistic as XX transpose. Then when we look at eta for the statistic, so the statistic is still mapping to a finite dimensional vector space, but it's just a matrix. And then if we look at the statistic, if we look at the natural parameter that corresponds to HMMs, it's all natural parameters with this sort of sparsity pattern, where the purple things are non-zero elements and the empty things are zero elements. And that tridiagonal matrix structure corresponds to this chain graph. I like this view because it makes clear that with this statistic, you can also consider more possible graphs, right? What happens if I keep adding edges to this thing? Like, I could end up with the complete graph or something like that. What would go wrong if I had the complete graph compared to a chain graph? Any guesses? Sorry? Yeah, that's right. Yeah, it would link future information, so it would lose sort of maybe our local semantics. That's right. It also presents computational issues, as we'll see in a second. So here's back to our chain model. If we think about the Lognormalizer, right? What is that? That's log sum exp of our density, where we have to sum over all binary configurations. And as you might guess, when this matrix is tridiagonal structured, so when we have this chain structure, we can evaluate this sum efficiently. There's a whole bunch of graphical model semantics of how you can think about complexity in terms of the graph that only works for the finite valued and Gaussian cases. But really, the point here is that to do this sum, we can do it efficiently. And what it ends up doing, it turns out you can think of this as doing the sum sort of zipping along that matrix. You can sort of sum out the leftmost node and then the second node and then the third node. And so you can think of this as sort of passing messages where to compute the sum over all configurations, I only have to do sort of local sums and propagate information. I won't unpack the details, but you've probably seen some version of that for HMMs. Here's the neat thing that I will unpack though. If you have a way of computing this Lognormalizer, we know that we should be able to use automatic differentiation to get expected sufficient statistics. And in fact, if you use what that's saying is if I use grad of this Lognormalizer, that'll give me these expected statistics. And moreover, these statistics, as these are binary valued, are just like the marginal probabilities of each node being on and sort of the pairwise probabilities. So, and what's really neat, if you think about evaluating this in your computer with reverse mode automatic differentiation, the forward pass of your reverse mode automatic differentiation is going to be evaluating the function a. So that's going to do that red message passing on the top. And then when you do the backward pass in backprop is going to look like passing messages backward to evaluate your expected sufficient statistics. So what's interesting about this is when I learned about HMMs, we learned how to write this bidirectional recursion directly. The alpha beta algorithm or the alpha gamma algorithm, or like all these different message passing things. But we can reduce many of them, certainly this one, just to automatic differentiation, where we just have to implement the Lognormalizer. To convince you that that is simpler than implementing message passing, really makes the bookkeeping much nicer. Here is, so in this AutoGrad package that we started in Ryan's lab, we have an example of an HMM, and this is how we write the Lognormalizer function. The details aren't important, but it's just a little loop walking the graph from left to right and just sort of doing local sums. We're doing it in log space for numerical accuracy. And then to get the expected sufficient statistics, we actually have a little EM algorithm in that example. You just do grad of the Lognormalizer. So I've started to write all of my probability libraries, my exponential family libraries, in terms of a minimal amount of stuff, where I just implement maybe the Lognormalizer and the statistic function, and then get everything else for free. So I think I might skip over this section, only to give you the briefest hint. So what about, so this is going to go really fast. What about maximum likelihood? You know, some nice things might happen there. If you think about writing out your log likelihood objective, indeed, things simplify quite nicely. And we give a name to the value of the maximum likelihood objective, the sort of the optimal value. We call that A star of mu. So you give it any, for example, empirical moment vector mu, and this is the value of the optimal of the log density at the optimal parameter. So gradient ascent has a really nice interpretation here, where it just looks like iteratively trying to match the moments of your model, sort of the model moments, the expected sufficient statistics, with the target moments mu. You're just always taking that difference and taking a step in that direction. Actually, a lot of algorithms have really nice interpretations. Here's a claim to go over very briefly. It turns out that actually the gradient of A star gives us the optimal, technical conditions aside, they're sort of easy to satisfy. The gradient of A star gives us the optimizing eta. So basically, if you want to do fast maximum likelihood and you have an exponential family that's tractable in the sense that you can evaluate A star, which you can in a lot of cases, then this is where you can get closed form sort of EM updates, if you like. So just to sit back for a moment, this is the convex analysis sort of rearing its head again. In fact, A and A star, even though we got to A star by just reasoning about maximum likelihood, they turn out to be Fenchel conjugate pairs. And these are like really canonical objects in convex analysis. And there's this really nice sort of, these mappings, the gradient mappings of A and A star are almost like inverse mappings of one another. And in some cases, they are essentially inverse mappings. And this unlocks a ton of algorithms that we can use where we're like iterating these things. Even better, if you just write your libraries to implement these functions and you have autodiff, you get a lot of algorithms for free. We'll see a couple cases of that. So here's a summary of exponential families. In terms of like how to write libraries, if you just implement the statistic function and the Lognormalizer function for a tractable family, so this is a family, these are like integral tables, right? Like integrals, unlike autodiff, integrals, you just have to have a table of them, the ones you can solve efficiently, right? That's just how the world works. But there are some integrals we can solve nicely, like the sums in a hidden Markov model, or the sums associated with integrating out the latent states of a Kalman filter or something. The idea here is that when you have these special distributions where you can evaluate these Lognormalizers, that's very powerful that you can evaluate these integrals exactly. And here's a way to set them up in your code libraries. You can just implement the statistic function and the Lognormalizer. That's basically populating your integral table. And that will give us access to exact inference, as we just saw, where we got the expected sufficient statistics. And actually, sort of to be implied soon, that'll also be enough to do mean field variational inference, even like structured mean field variational inference. If you write a Lognormalizer for your HMM and a Lognormalizer for your linear dynamical system, like your Kalman filter model, that'll be enough to generically implement structured mean field inference with autodiff. Sort of analogously, if you write down A star, which is a different kind of tractability, then you can get like variational EM for free, just all the different, all these different algorithms. And finally, if you want to draw samples, you might want to write a sampling routine. So this was all sort of a view about tractable families, when we can implement the Lognormalizer exactly. As maybe, hopefully it should be clear, when we looked at the binary HMM, convex does not mean tractable, right? Like you can encode all kinds of hard, NP hard problems in the problem of evaluating the Lognormalizer. But in some cases we can evaluate it. And so the next question is, what if we compose tractable families to make up intractable ones? How can we get approximate inference algorithms that exploit those structures? So back to mice. Remember, we wanted to model mouse behavior in terms of, we wanted to model a mouse video and discover sort of latent units of action. And now maybe we have some tools that might help us. Let me describe to you a model that sort of composes up pieces of tractable exponential families. So to start out with, let's imagine that we want to have a sequence of latent variables that corresponds to, at every time, at every frame in the video, what state the mouse is in, what behavioral state the mouse is in. So we can have a finite valued Markov chain, right? Just like an extension of the binary valued one. And the idea is that as time marches to the right here, the directed graphical model, it'll be in a particular state, like the blue state for a while. That'll be like when it's darting, and then it'll transition into the green state. Great, so we have a little hidden Markov model. That's a great way to start organizing the information in our representation of mouse behavior. What next? We want to connect this up to images ultimately. So what we can do next, really, this is my favorite model, by the way. It's called a switching linear dynamical system. And the idea is that we'll have this latent Markov chain, and each state of the Markov chain is going to correspond to a set of linear dynamics in a low-dimensional latent space. So these are like dynamics on our coordinates. So while we're in the blue state, we're going to be driving this linear dynamical system with some set of dynamics parameters, like this matrix A. Then when we switch to the green one, we'll switch to a new set of dynamics. And then again, switch to the red one in the Markov chain, we've got a new set of linear dynamics. So we have a collection of these linear dynamical models, one for each state. And each one is going to correspond to a behavioral syllable in a very nice, simple representation. We can even do things like if we wanted to put priors on these matrices, we could say, hey, I want to make sure that the dynamics aren't too fast, right? Like, you can think about what frequencies are included, are likely to be included in these kinds of matrices. So let's just clean this up into a graphical model. We'll use x's for so z is sort of the discrete state component. X is the is the continuous state component. We'll package up those matrices as parameters in this theta. And so this is a great start to our model because we've sort of written down the organized piece of how we're going to have discrete states, and those are going to drive simple dynamics. So the latent space is looking good so far. The question is, how do we connect these up to mouse images? And we're not going to quite get there yet, but that is the ultimate goal. I want to talk more about this kind of compositionality that we just saw, where we composed up simpler pieces to get a more expressive model. So instead of mouse images, for the moment, imagine that we just have linear Gaussian observations. And that'll play nicely. There's no neural networks here. This is just another iteration of composing nice sort of exponential family distributions in our directed graphical model. So the big question is, if we compose up exponential families like this, what happens? And in particular, can we get compositional algorithms that use the structured pieces that we built in? If I wrote down an HMM, I don't want to lose the fact that I can I can sum out the latent states of that HMM very efficiently. I don't have to fall back to like reinforcement learning and some kind of super noisy gradient for learning. I want to exploit that fact in an approximate inference algorithm. So here's the way to think about that composition. I'm just going to claim this, but if you write out some examples, you will see that this is true. This is how, when we build up those models in that way, like I just showed you, here's the kind of structure we get out. In fact, we get out, not always, but the natural way to compose these things. What you end up getting is a new exponential family in terms of, so think of the T1 and T2 here as each is the set of sufficient statistics for a tractable exponential family. So maybe T1 corresponds to the hidden Markov model over time, and T2 corresponds to the linear dynamical system unfolding over time. So the way these compositions work out is we get a new exponential family where the statistics are actually polynomials in the in the statistics of the components. So here you can see that we're just expanding out the statistic to be there's a monomial term on T1, a monomial on T2, and then we have this tensor product of T1 times T2. The tensor product just means sort of the outer product of these things. You can already see why this might be a nice structure. If you think about what would the distribution look like if you condition on x2. So if I told you the value of x2, and then I said only reason about the distribution on x1, what would that distribution look like? What would that density look like? So I'm going to give you a value for x2 and say, what's the remaining distribution on x1 look like? Any ideas? Yeah. Yeah. Yeah, super nice, right? You get to combine some terms. That's right. So the answer was if x2 is no longer a variable, you can throw away that t2 x2 term. And this term that combines both of them, we just look at that t2 x2 as a constant. So we get something like this. So actually read everything on the left as just part of the new parameter. So we see that we have t1 x1. x1 is the only variable here. We see that we have t1 x1. That's the statistic of our, the family, the exponential family on just x1, sort of in the prior, if you like. And then for a fixed value of x2, t2 x2 just becomes part of the natural parameter, sort of part of the energy function on that t1 x1. The notation here with the dot is kind of loose, some kind of tensor contraction. So that's right. So you can already sort of see why a polynomial structure like this one, in particular a multilinear polynomial where the maximum degree of any monomial statistic, t sub I, is just 1, so they all appear linearly, is nice. In fact, let's generalize this a little bit and just write it with arbitrarily many terms, but it's the same thing. Here we're saying that let's consider a big exponential family composed out of small ones, and the way in which it'll be composed up will be, we're going to say that the overall family is some kind of multilinear polynomial of the pieces. So and we're going to write G as that multilinear polynomial. So we're going to, multi-affine. Technically it's affine because if you plug in zeros, you might still have the constant term. But I'll probably keep saying multilinear because I forget. So all these betas are just binary indices telling you whether or not a term is included. And remember, we want to think about each sub little t as corresponding to a tractable family, but the overall family, the overall Lognormalizer corresponding to this big polynomial sufficient statistic will not in general be tractable. It'll be hard as soon as we compose up a few pieces. So if it's not tractable, what can we do? Here's just copying that form again. And I just want to give you a sort of flavor of how we can get, well, let's see. The question is, can we build algorithms for this composite family, this composed up family, like our composed up switching linear dynamical system that can do things like approximate sampling from this model via MCMC, or maybe I can approximate the expected sufficient statistics of this model, or even approximate or bound the normalizer itself. Maybe I can do variational EM. And I want to build these algorithms generically, sort of like automatically, and in ways that exploit the structured tractable parts, if I can. How do we do that? I'm going to show you 2 examples, and then promise you that actually a lot of different algorithms are unified this way. And once you see these pieces, you'll be able to work it out for yourself how to do it. So let's think about sampling first. I have these slides memorized because I just made them yesterday. Great. So let's think about sampling. Here's a claim to do with Gibbs sampling. So Gibbs sampling looks like I want to draw an approximate sample, but I can't do it all in one go. I'm going to do it iteratively. And if I have a partition of my variable x into these components like x1, x2, x3, up to xm, these could be blocks of the thing. A way I'm going to build my MCMC algorithm, sort of an iterative way to draw a sample, is I'm just going to resample each block conditioned on values for all the others. That's going to set up an iterative algorithm. And so the primary object of interest is, what do these conditional distributions look like when I look at xm, sort of the distribution on the mth block, conditioned on all of the others? That's what I mean by the little neg m notation. So here's this claim: Gibbs sampling is easy, or like sort of generic. Once you have this multilinear polynomial form, we can write it. This is basically using that idea that we saw a moment ago with the two statistics. We can say that the distribution of xm, given everything else, just looks like a version of the sort of prior distribution on xm, this little exponential family with the statistic t sub m. And that's one of our tractable families, so maybe we can sample from it efficiently. The trick with autodiff is that you can extract the natural parameter for this guy by using differentiation on g. So if you have a function that evaluates that multilinear polynomial g, we can just autodiff it, and that'll give us the natural parameter. And so what that means is, here's a way to write generic Gibbs sampling. If you specify your model in terms of g, the multilinear polynomial, and you give me a list of samplers, one for every tractable family, this is a Gibbs sampler. And it works for, if you wrote your basic probability function library the way that you should, right? In terms of just like write every tractable function that you can. If you wrote a sampler for each one, now you can generically implement a Gibbs sampling algorithm for the composition of these things. So this will sample your XLDS. It'll do something like this. Here's a sort of stylized version of the model. This will do block sampling, not just like single site Gibbs, but this will cycle through doing block Gibbs sampling. All you had to do is write that normalizer like I showed you for the HMM. That'll correspond to joint resampling not the normalizer. If you reason about the sort of tractable pieces in this way, you can compose up these kinds of algorithms super nicely. This is really satisfying to me because in grad school, I wrote a bunch of code that was just very specialized on the particular model. Every time I wrote a new Gibbs sampler, I'd have to write a new model. Whereas here, so long as when you compose up a model, you can get out the polynomial g, now you can implement everything generically. All thanks to autodiff. Let's look at another example. This one is even better. This one's my favorite because in the mouse project, we were doing variational inference. So variational inference, if you don't already know it, I probably won't explain it to you now, but here's the basic idea. We are going to approximate a sort of intractable distribution, our intractable distribution with the polynomial in the sufficient statistics with a simpler one. Here's a simpler distribution on x. Consider a distribution in which all the little x sub m blocks are independent. So we have a product structure. And think about every single factor as just being in this, in these tractable exponential families. In fact, just like we saw with the binary HMM, where when we put zeros in the eta matrix, in the natural parameter matrix, that ended up specializing us down to like a chain structured family. Analogously, this is actually, in some sense, contained in the original exponential family, the big polynomial statistics. We're just setting to zero, we're constraining to zero all the natural parameters that correspond to the cross terms, that correspond to anything other than ti, xi. So this is actually a subfamily of the original intractable family with linear constraints, in fact, zero coordinate constraints on eta. So here's a claim. It's very elucidating to write out sort of the regular variational, mean field variational lower bound on the evidence that we often see. Here's the sort of convex analysis perspective. It's to say that the intractable normalizer has to be greater than or equal to this expression, which is tractable to compute. So here's the idea. Take the sort of energy function from your intractable family, but plug in, instead of expected sufficient statistics in that original family, which you can't compute, plug in expected statistics from Q. And then we have this entropy term in terms of the Qs as well. And this is what we define, if you look on the very bottom right, as this variational bound in terms of our variational parameters eta. And if we choose eta to maximize this bound, we'll be approximating things like expectations of our target family. So this is actually not hard to show with the right inputs. It turns out to be a sort of clear, I think I have too much color on this slide. It turns out to be a clear consequence of this variational definition, variational characterization of the Lognormalizer that I flashed up briefly, which is to say that you can write it as the soup over all possible moments of this expression here involving A star. And the reason this is an obvious consequence is we are now taking the supremum not over all possible moments, but only the set of moments that's representable by our restricted family, where we constrain some of the natural parameters to be 0, some coordinates of the natural parameters. So this is an interesting perspective on the sort of classical variational evidence lower bound that we see all the time. One point to make is, even though I wrote it in terms of these A stars, and I said maybe you don't have to write that in your library unless you want to do EM or variational EM, that is true, and here is the same expression where I've just expanded out. Instead of using A star and mu parameters, I've written everything in terms of the natural parameters, eta. So here is a claim that will give us a generic implementation of structured mean field. If you've seen any implementations, including my own, of structured mean field for switching linear dynamical systems, they're super complicated. But this is going to give us a generic implementation of it using this sort of compositionality that we've built up. So here's the claim. I'm going to optimize that lower bound. I'm going to find the best lower bound, and that's the best approximate inference in my target family, by doing a sort of block coordinate updating procedure, where I'm going to optimize over each tractable statistic, eta sub m, separately. And here's the claim. You can get the optimal natural parameter by differentiating g. That's very analogous to what we saw before. And moreover, we know how to compute all the corresponding means. That's by differentiating the Lognormalizer. I think this is actually even clearer in code. So here's the way I write all my structured mean field algorithms now. So there's like a function within a function here. Let me read it for you because I think it's interesting. The inner function is so we see that we just define it in terms of G, which is going to specify how our composite model is built up of tractable pieces. We have a list of log partition functions called A's, and a list of initial natural parameters called etas. These are our variational parameters that we want to optimize. So we're going to write a function that does a mean field sweep as a function of a sort of set of moment parameter iterates. And all that means is we're going to go through our, for every m, we're going to get the updated natural parameter by differentiating g with respect to its mth argument. And then we're going to differentiate the corresponding normalizer. And this is automatically, if you just give me a way to evaluate these log normalizers, this is automatically going to be doing a sweep of mean field variational inference, structured mean field. Sorry, structure just means that we're using like the chain graphs, the chain subgraphs, and this sort of thing. To call that subroutine, we're given etas, so we're going to first turn those etas into mu's, and then we're going to run those mean field sweeps until they hit a fixed point. And that'll be sort of our optimal, a local optimum of the variational objective. These mu stars, we can convert them back into natural parameters at the optimum by using grad of g again. So this fixed point operator is something really interesting. I realized the one promise I made in my abstract was that I would show you how to efficiently differentiate this fixed point routine. Because when you embed, to peek ahead a bit, when you embed this kind of inference in a neural network architecture, so now you have this iterative inference within a neural network architecture, how can we differentiate through it efficiently? Do we have to like unroll it 10 steps or something like that? There's something much better you can do, and it's in a bonus slide. I didn't fit it into the main talk, so we'll see. If we don't get to it, I'm happy to talk about it after or something. Great, so this is a generic way to implement like structured mean field. You can write switching linear dynamical systems like this. Everything's great so long as you, I forget what the next slide is. Okay, so long as you give me your composite models by specifying this polynomial g. That's the way you're going to build up composite models. Just give me g, right? And I argue that that contains all the sort of conditionally conjugate models, all the things you've seen in the literature. They can all be written as a g. So just give me this g function, and now I've got all these great little code snippets. Here's the problem. It actually is really hard to write these polynomials. It's just inconvenient to write them. So here is actually taken from my code I think this is for a switching linear dynamical system, what the multilinear polynomial G looks like. This is not actually the entire sort of objective or anything like that. It's missing all these, all these normalizer terms. This is just the linear part, if you like. And there's like, library utility code being called. You can see that this is a polynomial because it's a sum of these einsums of things that look like statistics. But like, people, this is really hard to write. So I was really excited when I was like, oh, we can just write everything generically in terms of G. I'll just write all my models that way. And then I tried, and I got, to a switching linear dynamical system, and I was like, man, this is the worst. No one's ever going to do this with me. No one looks at this thing and is like, oh, I want to program that way. So that's too bad. The story doesn't have yet the happiest conclusion, but I'll tell you why there's reason for hope. It's a project. So here's a more natural way to specify. This is the full, no library code or anything, specification, except for like NumPy and SciPy, of the density for a Gaussian mixture model, right? And this is not super simple, but it's it's a sophisticated model where we're composing up a sort of like inverse gamma prior on the variances and all the stuff for a Gaussian mixture model. This is a more natural way to specify models, and even better is if you put a layer on top of this where you do some probabilistic programming. Somehow we want to, if we want to get these generic algorithms, we have to turn something like this into our multilinear polynomial G. What does that look like? By the way, I know this is natural because Matt Hoffman wrote this code, and so he must have written it in a good way because he's been doing this for a long time. So this is, if you like, the computation graph for that function, the sort of model energy function. I'm sure that is illegible to you, but I will just tell you at the top. There's sort of like inputs like pi and x and mu and tau. So like mu are like the set of means for our mixture model. And this is the computation graph. They're somehow specified in there amid this tangle of nodes is our multilinear polynomial. That's my claim to you, is that somehow it's in there. I just don't have it. I have the multilinear polynomial composed with the statistics functions. And we really want to get them separated out because I want to have that polynomial and like auto-diff it. But we have them composed together, and we want to decompose them. The decomposed version looks like this. And you can see these red nodes are einsum nodes. This is what I was writing by hand for a while. But this was actually automatically produced from the previous graph, which itself just came automatically from that NumPy Python expression. So this is a way, this system, we needed a way to automatically take those sort of like natural ways of specifying things and turning it into the multilinear polynomial so that we could get that separately. So the multilinear polynomial here is like, if you cut along the inputs to every einsum node and you hoist that graph out, that's the polynomial we're after. So this was this project called AutoConj, as you can see on the bottom. Not a great name. But the idea was, let's automatically detect and exploit the structure, even if you just write pure Python and NumPy programs. And the details here aren't super important, but it was fun, where we used some sort of like Python tracing techniques, some sort of pattern matching to rewrite the graph and like separate out this polynomial, write it in terms of einsums, and separate out the statistic functions. For more, please check out that paper. I think this method kind of failed, though, in that it doesn't scale enough. The sort of term rewriting approach doesn't scale to big graphs where you have like time series models and that sort of thing. I had an intern who did an incredible job named Matt Mackay. He was working with me, Matt Johnson, and also Matt Hoffman. So we had like a little clique of Matts. And my intern, Matt Mackay, did an incredible job extending the system to work on general graphical models, like the ones that we've been looking at with time series. And that works pretty well, but I think to really scale this thing out, we'll need a different idea. So this is you can check out the code online as well. It's some way to get automatically these polynomials, but it's not the complete solution yet. So here are our goals. Let's check the time. Hey, that's not a bad amount of time left. So we went through motivation. We went through talking about, hopefully you got a taste of not only the fundamentals of graphical models and exponential families, but also a flavor for how we can use autodiff and try to automate all these and make generic all these inference algorithms. I think that's going to be really critical. Just like autodiff was key for deep neural networks, I think we still need to push these things further and make them automatic so that anytime you want, you can sort of pull in graphical model technology and use it in your research. We're not there yet, but I want to switch back to talking about models and sort of inference architectures that build on all of that technology. Plus, here's where some deep neural networks will come. And again, my goal here is not to tell you that this is the answer, and isn't that cool? It's really to say, like, here are some ideas. Hopefully, they will be more obvious to you now that you've seen the first part of the tutorial, and I hope that you can come up with better ones. So I'm going to focus on the ideas that I know the best. I'm not going to cover all the literature. So remember our problem. We have this nice model, this sort of switching linear dynamical system model in our latent space. We thought that was a great way to describe sort of mouse dynamics because we had these like switching behaviors. Each behavior was like a simple dynamics model in the low dimensional space, but we needed to hook it up to images. How are we going to generate images from this kind of a model? And the answer is to use some kind of deep neural network. So if you're familiar with variational autoencoders, this is very much in the spirit of variational autoencoders, both more PGM graphical model stuff going on in the latent space. In particular, this is like a decoder architecture. So if you like, we just built an interesting, intricate model for the latent code over time, and now we're talking about how to decode that latent code into images. Oh yeah, when we draw boxes around things, I may have already done it. That just means we've repeated this part of the graphical model many times for like many different data examples. I'm probably going to start using that in these slides. So here's a simplified version of that model. I want to distill it further, at least the notation for it, just to simplify things. The structure is still there behind the scenes. Let's distill this by getting rid of time. Maybe it's still there, but we're just not paying attention to it anymore. And even getting rid of the fact that there's multiple sets of latent variables that we might want to treat separately. So what we have left over is this kind of a generative model class. These are the ones that we studied in our work. And I really don't like this word conjugate anymore, but that is the word that I used when I made these slides. So the idea is we have this nice multilinear polynomial exponential family structure in the latent space, sort of on theta and on these x's. And then our likelihood function is going to be something like a neural network decoder. So that's an interesting model class. In fact, I want to underscore that it's not just for switching linear dynamical systems. The ideas that I'm going to tell you, I haven't tried it, but I think naturally extend to a whole library of graphical model structures, and there are interesting ways to maybe compose them up with neural networks to make things like generative models. So here's just like a whole bunch of models, variants, and other kinds of things. Really, this is an open-ended space, and the algorithms that I'm going to show you are quite generic. So how do we do inference? Once we've built up this model with the PGM and the neural network decoder, the question is how to do inference. So first, I'm going to start by saying, reminding us, how would sort of inference look if we were just using linear Gaussian observations? So this is going to be a different algorithm from the ones we covered before, but it's going to fit into that framework. I just didn't show you exactly how. This is going to be sort of the stochastic variational inference that Matt Hoffman and others developed in the early 2010s. So how does this work if we have nice linear Gaussian observations? The variational family we write down, the structured variational family, might look like this thing on the right. You can see on the left we have a directed graphical model, and on the right we have an undirected one, which is, I think, the natural way to think about these things. Here is that same variational lower bound, but written in maybe more familiar kinds of notation, just in terms of the densities, not in terms of the, if you unpack the exponential family definitions. So this is the thing we want to optimize. To do inference in our posterior, we're going to approximate the posterior with this variational distribution, and we're going to do it by maximizing L over these separate natural parameters. So the way SVI works is really interesting. The idea is that ultimately this is because we have like many mini batches of data, we're going to distinguish between the local latent variables x and the global latent variables theta. And we're going to think about optimizing out the local latent variables. should also feel like a fixed point kind of thing. We're going to think about optimizing out the local latent variables corresponding to optimizing out eta sub x, so actually the parameters for the local variational factor. And we're going to define the SVI objective to be the one argument function that just depends on eta sub theta, that is the original objective, but where we plug in the optimal variational factors. I can do that. And what Matt Hoffman and his colleagues showed is that you can actually get gradients of this objective, even though it's partially optimized out. In fact, you can do better. You can get natural gradients of this objective. Natural gradients are great because they're sort of curvature corrected. They're kind of preconditioned gradients that take into account curvature from the variational family. So they can converge much faster. So that's good. Another interesting fact that this work showed is you can actually compute natural gradients of this partially optimized objective faster than you can compute flat gradients. Somehow you don't need to do as much work. So that's this natural gradient SVI, and if we add boxes around everything, so we're going to imagine having lots of video examples, and maybe we're subsampling mini batches, we can write the natural gradient this way, and so this can very nicely be Monte Carlo approximated to do stochastic gradient when n is very large. So that's great. That's this SVI thing. It's all super nice algorithms of the kind that we've unpacked in detail. Let me just say a bit more about what these algorithms look like when you're running them on data, like sequences of observations. So you're going to sample a mini batch of observations. You're going to condition using your generative model. You can actually just compute what the conditionals are, the sort of local conditionals. That's going to give us evidence potentials on every node. That's the first step. The second step is we run fast message passing. So this could be the fast hidden Markov model algorithms or like Kalman smoothers. These are some of the best algorithms that man has ever created. Like your cell phone is running Kalman filters all the time. These things aren't going to go away. So we're using fast message passing algorithms. And then step 3 is actually there is no step 3. Turns out we can compute, we can write a simple expression for natural gradients with respect to the parameters shown in orange here, just in terms of those values we computed. So that's how everything works in the nice hunky-dory world when you don't have neural network decoders. Let me briefly say a couple other things that are nice about graphical model land. You can compute arbitrary inference queries if you have partial observations or something. That's no problem. Great. So what goes wrong when we have a neural network decoder? I've used red to indicate that something bad is happening. Bad for inference algorithms, so difficult to deal with. So let's push this forward and see what happens. Can we do Hoffman et al. Style stochastic variational inference, partially optimized, get our natural gradients, that sort of thing. So we're going to write a variational family in the same way. We're going to define an objective. But you can see now that we've written this objective, before we had this p of y that folded nicely into the polynomial structure of p of theta and x. And it played in nicely. Now it's kind of like it stands apart because there's some complicated neural net business going on inside of it. So we can still define this variational objective. I've colored the variational objective in red because we can't even evaluate it exactly anymore. We can only sample, you can only do Monte Carlo samples, whereas before we could at least evaluate the objective exactly. Here, without even data subsampling, we have to sample to evaluate it. So let's try to do SVI. What we would have to do is define that partially optimized out version where we say choose the optimal local factor. And the reason I'm talking like this, that it's stressful, is that solving this problem is like solving a generic stochastic optimization problem. And this is the sort of thing we want to do in the inner loop of our optimization. So that's not going to be easy to do. And then finally, the SVI objective that we wanted to write down, the single argument version, is hard for multiple reasons. Maybe the main one is that we can't compute this optimal local factor anymore. So this is actually the state of things before variational autoencoders. This is a view of the problem that variational autoencoder solved. What can we do? We can't just solve stochastic optimization problems as a subroutine in our learning procedure. What can we do instead? The solution is brilliant, amortized inference, super cool. Here's a simple view of it. An even simpler model. This is the variational autoencoder model. So now we just have IID latent variables. This is the first vanilla VAE. The idea is that all we need to do is spit out some variational factors for our local latent variables x. Before we were choosing the optimal latent variable factors given our model, and we were like conditioning on it. But we can't do that anymore because our observation model is too complicated. What can we do instead? It is actually just a function, right? From your data, if I give you a mini batch of data and say, what do you think the latent variables are? That's some function from your data to some variational parameters. And so you can just say, well, I'm going to fit a function approximator, a parametric function approximator, that's going to take in data and spit out variational parameters. And it's only going to have 10 layers, so I know how long it'll take. So that is the sort of technique of amortized inference, where you have these inference networks that take in observations and spit out variational factors just in sort of one go. Then the objective that you write down is something that looks like this. So we're defining our local variational factors as just some function of the data, and these now sort of inference network parameters that I've written as phi, reusing the notation. And now we can just think of our variational autoencoder objective as just saying fit, fit my model. I should have written gamma, not eta sub gamma. Just fit my model and fit the inference network at the same time. So that's VAEs. I want to underscore that that was the most vanilla kind of variational autoencoder, but there's a lot of different kind of inference architectures you can come up with, including ones that use ideas from graphical models. So this is actually not my work. This is just a subsample of some things. So for example, you could imagine a sort of CRF kind of approach that takes in those observations and spits out the natural parameters of your graphical model sort of in one step. That's a great idea, very, very CRF-like. You can also imagine approaches that just take as inspiration message passing, but don't actually necessarily use the graphical model structure. So like, hey, why don't we just fit a bidirectional RNN as our inference network, and maybe that'll do a great job. So there's a lot of different architectures you can have for inference network. The work that we did was sort of focused on making the most general and the most sort of like structure exploiting version of these inference networks. So I'm going to tell you a bit more about that. So let's review. When we had this natural gradient SVI procedure, things were nice. They didn't work for general observations, but when it did work for things like simple linear Gaussian observations, we had all these nice properties. Variational autoencoders, on the other hand, we love them because I feel like the first bullet is the most important one by far, so don't count the bullets here. But variational autoencoders let us solve this sort of more general inference problem by saying, let's just learn a function approximator that does inference for us. The downsides to that are now, in particular, I think that third one maybe is the most salient. Now we're relying on this inference network to do all of the inference for us. Not just the hard part, like reasoning about images, but it's really doing everything, like smoothing over time and this sort of thing. One other limitation is that there's a limited set of inference queries you can make, potentially. Like maybe you can't deal with all different partially observed data patterns. So our structured VAE work, structured as in structured mean field, like graphs inside, was really an attempt to put these two things together, like chocolate and peanut butter, and try to retain as many of their strengths as possible. So let me just give you a high-level overview of what that looked like. Here's again our setting with sort of linear dynamical system, nice latent variable model, but a difficult decoder. If you think about what the challenge is, it's really that we have these tricky evidence potentials that look, if you think of this is sort of the evidence potential that you get for data y, looked at as a function on x, are sort of latent variables. And these things are just too complicated, so we don't know how to deal with them. These are the only hard part. We don't actually need to, for example, have our recognition network output the pairwise potentials. We can derive those interactions from our generative model. It's really just these observation terms that are problematic in this case. So our idea in SVAE architectures was to say, why don't we just learn a way to approximate the potentials that we don't know how to deal with, and for everything else, we will sort of derive the inference from our generative model. So we'll have to learn the minimal amount possible, and we'll be able to leverage the maximal amount of structure possible. So basically the idea is we're going to replace that difficult term in red. I should have made these slides more friendly to color blindness, but we're going to replace the difficult term with this psi term that itself is going to be a function approximator fit to data. So the view is we're going to say those difficult potentials, we're going to learn how to approximate them as a function of observations by something simple like a Gaussian potential, and then we're off to the races. We're back in nice, happy graphical model land. So in fact, we can sort of define the objective nicely, where we're going to sort of like do inference as if we were in a nice graphical model world, and then that's ultimately just our architecture for outputting our beliefs on the latent variables. So I just want to give you a flavor for what these algorithms look like. You sample a mini batch of data, like before. Unlike before, you then apply your recognition network to get nice evidence potentials. And now, really the difference between this and other works is that you just get maybe evidence potentials that are nice, and then you're off to the races to do all kinds of inference algorithms. Shown here, a sort of fixed point iterative switching linear dynamical system iteration that you can run. Then we can actually, as we show in the paper, get fast, sorry, wrong one, that was step 4. Step 3 is you can sort of sample what you need to and generate flat gradients for updating the neural network. And then you can use what you've already computed to compute natural gradients for sort of the nice parameters. So, you know, we try to include these two things as special cases. So I'm going to try to wrap up. I'm trying to remember how much I have left. We'll see. I think we have 10 more minutes, but I want to have just a couple minutes for questions. So let me show you some fun videos. This is that pinwheel data set. On the left is the data space, on the right is the latent space, and the encoder-decoder pair are initialized to be identity. And we've put a Gaussian mixture model prior on the latent code, and we're going to do all of our fancy, you know, latent, fancy structured variational inference on the Gaussian mixture model part. And you know, fit the neural network with gradient descent. When I hit play, it's very satisfying what happens. We've even used like a Dirichlet process to learn the number of components. And you can see, as hoped, we've learned a sort of complicated density model in the observed space on the left. And on the right, we've learned how to organize, you know, the neural net has done for us, learned how to organize a space so that our Gaussian mixture model prior fits well. Here's another video to do with sort of linear dynamical systems over time. I'm going to skip it in favor of trying to get to questions, but I will play it because it's very satisfying. It's like learning to organize the latent space so that it looks like a linear dynamical system. It's able to make good predictions. So I guess one big picture takeaway is I think there's really a spectrum of broadly speaking, not just our work, but sort of these graphical model structure exploiting variational autoencoders that use different amounts of sort of exponential family technology. And as you sort of use more technology from exponential family world, you can use less of you know, learned inference networks. But, you know, it's up to you where to set that dial. So I'll just briefly tell you about how we were able to use this on the mouse data. So if you fit, I guess these are raw image frames. I'm not sure how reasonable those look, but these are just raw. You know, the mice look like little sort of beans where you can sort of see their head and their ears sometimes. This is just a bunch of random image frames. If you fit a variational autoencoder and you just sample from it, so this is just plain VAE. I'm going to like increase the sophistication of the model progressively, and you draw samples. The samples look like this, and I'm sure to you, but also if you look closely, these look essentially the same. They're just sort of like denoised versions. So like VAEs are really good at learning the image manifold of these, you know, simple mouse depth video images. So that's great. Let's, you know, add the complexity of the model. Oh, this is really nice as well. If you take, you know, different, you know, 2D planes, like random 2D planes in your latent space, and you make a grid, a sort of integer lattice on that plane, and you decode those points, you can get these nice plots where you can see how the latent factors are like explaining the mouse image. And you know, I made a bunch of random ones and then chose one that was the easiest to interpret. But this is really nice. This is, you know, what we see from variational autoencoders, where in the top left, this is the mouse actually sort of balled up, and you can see these little ears sticking out. And as you move to the right from there, he's sort of elongating his body, and you move down along this axis, he's sort of raising his head up. So like this is a really nice, you know, way of modeling images. Then you could say, let's fit not just IID Gaussian latent codes, let's fit a latent linear dynamical system and see how well it predicts into the future. And what we're seeing here is on the, on the bottom rows, those are real data. And then on top rows, that's sort of generated data. We're conditioning on the frames up until the red line. So that's kind of like a reconstruction. And then past the red line, we're just predicting the future. And these frames are actually subsampled. So I think this goes up to like 100 or 150 frames out. So we're able to generate very coherent looking mouse videos from these kinds of models. If you look closely, you can see that it's generating a very plausible continuation of the mouse's sort of smooth dynamics. So time series model's looking pretty good. And then we fit the full switching linear dynamical system, and we were able to discover automatically a lot of interesting behavioral modes. Several dozen. I'm just showing you some of the some interesting ones. This is a panel of a bunch of examples of when a particular behavioral syllable was used. And when the white square turns on, that's when we enter, syllable number 32 or something. And 32 is what we can interpret as the start of a rear. You can see the little mouse's head sort of go up high. There's also things like falling from a rear, right? All these different mouse videos, they're doing different things, and then when the white square turns on, they're all falling out of that rear. Here's a really interesting one they were able to find. Though you might not see what it's doing unless you're used to looking at mouse videos. This is grooming. So this is sort of like the mouse is balled up and he's sort of grooming his tummy. You can see his little ears wiggling when the white square turns on. We were very satisfied that we were able to find this grooming state. And indeed, the scientists, not me, but the scientists use these kind of representations to do really interesting science. And they zapped the mice with lasers and did all their fun stuff. I won't talk about the details, but even we could look at things like we could recover what drugs we gave the mice. We gave the mice some crazy things, and then we could tell what dosages we'd given them, even in a using a sort of like unsupervised representation and feeding it into a simple classifier. We could recover all that information. So these were our goals. I hope that you agree that we covered some of them, and I hope you also agree that we did not cover the non-goals. But let's see, that's about it. One quick aside, what I work on most of the time now, I hope you've been admiring my sticker on my laptop here, is this system called JAX, which is a way, actually, honest to God, it started out as an attempt to implement SVAEs better. And then it grew into this sort of thing. So it's sort of a system for automatic differentiation and use of accelerators. I think it's very flexible, and so it's going to be good for these kinds of new architectures and a lot of other things. It is all on GitHub and developed in open source, so take a look if you're interested or talk to me afterward. I'd be happy to give you a sticker. So that is everything for the tutorial. I think we have 2 minutes for questions, or I will be here all day and happy to answer questions. Thanks for your attention.